Welcome to Lecture 8, the Doppler effect in blackbody radiation. So in the last two lectures, we focused a lot on light, first as an electromagnetic wave, then as a particle, and then in the latter half of the last lecture, we introduced the concept of spectra and focused on the three types of spectra: continuous, emission line, and absorption line spectra. And all of this has been sort of aimed towards the same fundamental goal, which is extracting as much information out of the light that we can obtain as possible. And so the goal is to figure out things like what are the stars and what are the gases in interstellar space made of, what are their pressures, what are their temperatures, and so on. And so to continue that, we're going to step now into the realm of the Doppler effect in blackbodies and try to understand even further what things can affect the types of light that get to us, and how can we use that light again to disentangle as many properties as possible about the stuff that's out there. So let's give it a go. So we're going to begin today with a discussion of the Doppler effect, and this is something that you may be familiar with, you may not, but the Doppler effect is something that it's a property of any kind of wave, it turns out. And so this is something certainly that is true of sound waves, and you may have encountered, well, you certainly have encountered it, but whether you've thought about it or not, I don't know. So today we're going to focus, not surprisingly, on the Doppler effect in the context of light. But again, if it's something that you're familiar with in other contexts, it should be fairly straightforward to make connections there. So first, we'll kind of start with the end game, and then we'll kind of discuss what leads up to that. So a star's light will be blue shifted if the star is moving towards you. And in particular, this means that its wavelength, the wavelength of the light that you will observe, will be shorter than it was when it was emitted, from the star's point of view anyway. Similarly, if a star is moving away from us, then its light will be red shifted, or its wavelength will get longer. And it turns out that a diagram actually does a pretty good job of clarifying why this would be the case. Imagine that you have a star here which is emitting light equally in all directions, okay? And as we discussed in our last lecture, the light emitted by a star is at least very nearly a continuous spectrum, but we'll focus on a particular wavelength. So say, for example, focus on the peak wavelength in that star spectrum. So if it's the sun, then it's peaking in the yellow, and so we'll focus on a yellow wavelength. Well, as the star emits light, it emits, waves. We think of light as a wave typically when it's traveling through space. And so it's got, as a wave, it's got peaks and it's got troughs. It's moving in a sinusoidal way. And so in this type of diagram, every time you see a ring, that represents a peak or a maximum of that wave. Okay. Well, what's happening now is, so every so often it emits a peak, and so it's got concentric rings that represent the peaks of of that light. Similarly to if you dropped a pebble into a pond, it would create water waves, and there would be concentric rings as you drop different rocks. So, but what you observe, the wavelength, then, is the distance between these rings. Okay. So if the star is at rest and just emitting light equally in all directions, then the wavelength will be measured to be the same regardless of where you are in doing that measurement. But if the star is moving, that's not true. Because if the star is moving to the right in this case, then it will emit some light, and that light will start traveling out. But in between that first peak emission and the second peak emission, that star will have moved somewhat in the direction of the peak, of one of those peaks. And so when it emits that second peak is actually a little bit closer to the first peak than it would have been if the star were at rest. And so the result is that the wavelength that this observer out here on the right will measure will actually be shorter than the wavelength that the star emitted at rest. And if the wavelength is shorter, that means that we perceive that light as bluer. Thus, in the spirit of not being very creative in our naming schemes, we call that blue shifted. And the exact opposite of true is true of an observer from whom the star is moving away. So if the star is moving away, then it emits a peak, and then it moves away, and then emits another peak. And so the distance between those peaks, the wavelength, is actually a little bit longer than it would have been had the star been at rest. And so since the wavelength is longer, the frequency is lower, and the color will be redder, and so we call that redshifted. And so the upshot is that when a star is moving towards us, the light will be a little bit bluer than it would be if it were at rest. And if a star is moving away from us, it will be the light that we observe will be a little bit redder than it would have been if we were at rest. And as you might have gathered by now, we can actually use those observations to figure out how is this star moving. One thing that's important is that we can only measure something called the radial velocity in this case. So in other words, we talk about a star moving towards us or away from us, but stars can also have what are called tangential velocities. So they're not going to be moving just directly towards us or directly away from us. They'll be moving at some angle. And so the Doppler effect gives us some insight into what we call the radial velocity, which means the speed that the star is moving either towards or away from us, but it doesn't give us any insight into, again, what we call tangential velocities, which means kind of velocities, in the line perpendicular to that radial velocity. So as I mentioned, the Doppler effect is something that applies to all sorts of waves, not just light. Here in astronomy, we're mostly concerned with light, but the Doppler effect certainly applies in the case of sound waves as well, and most notably affects the frequency of sirens of police cars or ambulances or anything like that as they move past you. And so no doubt you've noticed the apparent change in the frequency of a siren as it approaches you and then recedes from you. And I've embedded a short 3-minute video from YouTube that does a good job summarizing that and kind of rehashing some of what we talked about in the last slide. So I won't play that for you here as I narrate because it's got its own narrations. But I certainly invite you to review that just to kind of further drive home the fundamental aspects of the Doppler effect. So what does the Doppler effect look like? So what do we mean by that? So the claim that I've made is that by understanding the properties of light and by understanding things like the Doppler effect and how it affects how, in this case, the velocity of a star relative to us impacts what we observe from that star, we can actually use that knowledge to extract information about the things that we're observing. So at the end of the day, what we're really interested in is, since we're going to be observing spectra of stars, we want to know, well, how does the spectrum of a star change based upon that star's speed? So there's a great applet here that I've included that, again, I won't try to use dynamically. We're in real time here as I narrate because I think it'll be more effective if you play with it yourself. But it's a cool tool which allows you to change the speed of the star relative to the Earth and change the direction, in terms of making it move towards you or move away from you. And then it will show you how the spectrum of that star here at top changes relative to what's called the reference spectrum, which just means the spectrum in the case where the star is at rest relative to the Earth. So pause me as long as you like, as long as it's not infinitely long, because we've got to get to the end of the semester at some point. But I think this will be a useful tool to sort of give you a sense of how does the spectrum shift, how does it change as a star moves faster or more slowly, either towards or away from us. So the first question that I want to ask is, which direction will the star's spectrum move if the star is moving toward Earth? So we've introduced the terminology of blue shifted and red shifted. And we've already said that as a star moves towards the Earth, a wavelength will be blue shifted towards the blue end of the spectrum. So as we look at the complete spectrum of a star here, but with the continuous background and the missing absorption line spectrum, the question is, how will the totality of the spectrum look if a star is moving towards the Earth? Well, here's the answer. As we've already said, if a star is moving towards the Earth, it will be blue shifted, which means that any given wavelength will be shifted towards the blue end of the spectrum. And for the same reason, any missing wavelength, any absorption line will be shifted towards the blue end of the spectrum. And so if you look at a particular wavelength, so for example, there's this hypothetical star that we're analyzing its spectrum, and we say, aha, I see a missing line here here at 590 nanometers. So this is the observed wavelength of an absorption line in the star's spectrum. So one thing that I would typically do, right, if I, based upon the expertise I've developed over the last couple of lectures, I would say, well, one of the things I'd like to know is what is this star made up of, okay? And I'm interested in knowing what elements are in the atmosphere of that star. Well, one way to figure that out, in fact, the way to figure that out, is to look at the absorption lines in the spectrum and figure out what atom has an absorption line of this wavelength, right? Because I know there must be some atom which has an atomic transition corresponding to 590 nanometers, because that's the only way that this wavelength would get taken away from the otherwise continuous spectrum. So what I would do is I would go to my catalog of atomic fingerprints, if you will, and look at the wavelengths either that would be absorbed by any given atom, and I might start to get confused because I would look at the atoms that I know are likely to be there, and I would find nothing at 590 nanometers, and so that would make me pause, right, and say, well, I know that the only way that a wavelength is missing from the spectrum is if it's been absorbed. And the only way that it can be absorbed is if an atom has a specific atomic transition whose energy corresponds to this given wavelength. So how on earth can it be that there is no such transition? Well, the answer in this case is that the star is moving relative to us. And so while I observe a 590 nanometer wavelength, that's not the wavelength at which the star actually emitted that light. It's been shifted. And it's been shifted, in this case, from what we call the rest frame wavelength of 600 nanometers. So, for example, and unfortunately this makes my job quite a bit more difficult as an astronomer, because it means I can't just look at the missing wavelengths and then compare them to my known atomic transitions. I have to compare them to the known atomic transitions with the caveat that they may be shifted somewhat based upon the relative radial velocity of this star. But the good news is that if I can find a wavelength that's close to my observed wavelength, and then I can use that in order to both determine not just what the star is made of, but also how fast that star is moving relative to us. The other thing to keep in mind is that this relative shift will be the same for every wavelength, right? Because any given atom has some certain number of atomic transitions that will be observed here in the visible spectrum, right? So there are lots of lines, but each one of these lines will be shifted by virtue of the velocity that the star is moving. And that shift, the velocity of the star is the same regardless of what the wavelengths are. So it definitely makes the process of identifying the composition of the star and its velocity more complicated. But the good news is that once you've done it, you get even more information. So how do you actually calculate the velocity of the star? Well, the good news is there's an equation for that. And the even better news is that you're not actually going to need to plug into that equation because, as I have said before, this is not a class dedicated to a whole lot of quantitative analysis. If you're interested, I'm certainly happy to talk about it, but you can't say I didn't show you the equation. here it is, and it gives us the radial velocity of the star relative to us as a function of the speed of light, c, and then in terms of the both observed and the rest wavelengths. So again, in practice, to make the identification of the rest wavelengths, there's a bit of artistry there. Of course, in practice now, what you would do is you would write a computer program to do this work for you, to make it much less labor intensive. But the observed wavelength is just what you observe. So that's the measurement that you make here on Earth with your, with the apparatus that we've described in prior lectures. But the rest wavelength is something that would take a little bit of work to get to, because you don't know that right off the top of your head, because again, you don't know what this wavelength is. Now, it's important to know, though, there are certain wavelengths that you know will be present in every star. There are certain spectral lines that you know will be present. For example, hydrogen is present in the atmosphere of every star. And so any star that you see anywhere in the universe will have an absorption line corresponding to the hydrogen which is in its other atmosphere. Similarly, there will be helium in every star. And so that helps a lot, because there are certain wavelengths that you know need to be present. And so you can look at the lines that are kind of near where the hydrogen lines would be and say, this very strong line in the red end of the spectrum is obviously a hydrogen line. How much do I need to shift that in order to make it line up with where I know the rest the rest wavelength for hydrogen would be? And so, for example, given the detailed example that I have here, if the observed wavelength is 590 nanometers and the rest wavelength is 600 nanometers, you plug in the numbers here and you find that the radial velocity of this star is -5 times 10 to the 6th meters per second. So 10 to the 6th means a million. So this is -5 million meters per second, which sounds pretty fast, but it turns out that can happen in the universe. And the negative sign here means that the object is moving towards you, or in other words, the spectrum has been blue shifted to higher energies than it would have been in the emitting star's rest frame. So now that we're experts in reading star spectra, let's look at an example. So I'm going to give you, I'm going to read the question for you, just to make myself useful here, and then I'm going to pause as usual for 30 seconds or so to give you a chance to consider carefully. So at the very top here, you see the rest frame spectrum of a given star. So in other words, this is telling you this is what the spectrum will look like if you are sitting at rest relative to that star. So neither you nor the star are moving. So you know what that is, and now you observe, say, 5 different stars that are identical to one another. So they all have the same rest frame spectrum, but you make 5 different observations, and the spectra that you observe look quite different. A through E, these are obviously different spectra. And so the question is, which one of these things is moving fastest? Okay, so remember the question is then how are these things shifted? How is the spectrum shifted or changed based upon the relative velocity? So I'll give you 30 seconds here, and again, as always, you can always pause and take however much time you like, and then we'll come back and discuss it. Okay, so if you think back either qualitatively, or if you really like math and you love the equation, you can think back in terms of the equation that we just discussed in the last couple of slides. The faster a star is moving, the more the spectrum is going to be shifted, right? And if the star is moving towards you, then it will be blue shifted. which means that all of the spectral lines will be shifted towards the blue end of the spectrum. Conversely, if the star is moving away from you, then they will be red shifted, and so all of those spectral lines will be shifted more towards the red end of the spectrum. And so, for example, even before you answer the specific question that's asked here, you can go ahead, kind of go down the list here and see that, well, you know, A is obviously blue shifted. You know, all of these lines are shifted towards the blue end of the spectrum. B is red shifted, and so A is moving towards you, whereas B is moving away from you. C looks as if it's at rest relative to you. If you compare C to the rest-frame spectrum, they look very similar, you know, essentially identical. And then you can make the same comparison with D and E. And so to answer the specific question here, then A is actually moving towards us the fastest, you know, which is the question here, because again, it is blue shifted, and it's blue shifted more than anything else. If you look carefully, you know, again, we said that C looks as if it's at rest. D is a little bit red shifted. E is blue shifted as well. So A and E are both moving. Those represent stars moving towards us, but A is blue shifted more, and so it's moving towards us the fastest. So, you know, at the risk of beating a dead horse, you know, or playing, you know, the best rendition I can of a broken record, our job as budding astronomers is to extract as much information as possible out of the light that we receive as we can. And one of the things that I've mentioned, and one of the things that we'll be most interested in, you know, throughout this course, in terms of an attribute that we can extract from the light that we observe, is data related to temperature. You know, we're interested in what are the temperatures of the things, in particular the stars that we observe. And so let's think a little bit about what affects the temperature of a star, or anything, you know, for that matter. So the temperature of an object is determined by a property known as thermodynamic equilibrium, or thermal equilibrium, which is just a fancy way of saying a balance between heating and cooling. And so if an object is at a constant temperature, so not changing over time, then that means whatever energy it's absorbing from its environment is balanced exactly by the amount of energy it's giving up. Okay, so one thing that's important when we talk about equilibrium, and we're talking about thermal equilibrium here, but it's true of chemical equilibrium for those of you that have taken astronomy. It's true of mechanical equilibrium, any kind of equilibrium this is true of. It doesn't mean that nothing's happening. It just means that whatever energy is being absorbed is exactly canceled out by energy which is being emitted. And while we'll be mostly interested naturally throughout this class in the thermal equilibrium of stars, it turns out that any object can be in thermal equilibrium. And so, for example, the human body, your body, my body, everybody's body, is in, at least very frequently, in or very near a state of thermal equilibrium. And so, for example, any object that is at a non-zero absolute temperature, which means every object, and we'll talk about that in more detail here shortly, gives off a specific spectrum of wavelengths. So again, we're going to focus mostly on stars, but it turns out that you can determine any object's temperature based upon the electromagnetic spectrum that it gives off. And anything that's not at absolute zero does give off a spectrum. So again, your body does. And in fact, this is how night vision goggles work. So it turns out that the human body exists at a temperature, at least if it's living, that emits radiation in the infrared. So we're emitting radiation at all times, but it's invisible. And so, you know, if it's dark, if it's night, then, you know, we're not reflecting any light because there's no light from the sun coming to reflect off of us. And so all of the wavelengths of electromagnetic radiation that we're emitting are invisible. They're in the infrared. Night vision goggles work by basically absorbing that infrared light and then converting it into a visible wavelength. And so, you know, you don't look That's why if anyone has seen night vision sort of technology, seen the results of that, it doesn't look quite realistic in some sense, but there's no doubt that you can see, that you can see with it. So the technology there is cool, and we could spend some time talking about that. But for right now, the important thing is just that stars happen to be hot enough that they give off light in the visible spectrum. Okay, so that's obviously important because we can see that. But fundamentally, everything else gives off light just like stars do. If you're hotter than a star, you give off more energetic light, at higher frequencies and lower wavelengths. Conversely, if you're like us and you prefer to exist at a lower temperature than a star does, then you're going to give off longer wavelength, lower frequency radiation, and so it will be invisible, but nonetheless it's still there. So if you think again about thermal equilibrium, and we'll think about the Earth right now. So imagine this is the sun giving off its light, and then the Earth is absorbing some of that light, some of the light that is incident on it. There are two things that are happening, right? So the sun's energy is being absorbed by the Earth, and then the Earth, because it's at a non-zero temperature, it's also emitting energy. Okay? And in thermal equilibrium, those two rates of energy absorption and emission exactly balance each other out. And so this is kind of just a diagram representing thermal equilibrium, where you're absorbing light from the sun, and that energy is exactly canceled out by the radiation that's being emitted. On the other hand, you could have a situation where, again, you're absorbing the same amount of energy, but if the Earth is colder, then it will be emitting less energy. Colder objects emit less energy. That makes sense. And so what's going to be happening in this case is that the planet will be heating up, right? And so our side of the Earth does this in the mornings, right? Because it starts off, we're cold throughout the night. We turn around, the Earth rotates so that we're facing the sun. All of a sudden, we're able to absorb more energy, and because we're cold at this point, we're emitting less energy than we're absorbing, and so the planet heats up. Conversely, we could have the opposite situation where you're absorbing some energy from the sun, but you're very hot, and so you're actually giving up more heat than you're absorbing. And in that case, the planet would cool down. And again, this would be true of anything. It wouldn't have to be a planet. We're just using a planet here as an example. But thermal equilibrium, to sort of come back to the main concept here, is just a state where the rate at which you are absorbing energy is equal to the rate at which you are emitting energy. And if those two rates are out of balance, then you're going to either heat up or cool down, depending upon which rate is greater. So now that we understand thermal equilibrium, let's talk about another concept that you're already familiar with, at least to some extent, but we may be going into a little bit more detail here, and that is temperature. So you have an intuitive sense of what temperature is, because you certainly think about it. This is one physics concept that you think about on a daily basis. But at a microscopic level, what temperature actually is a measure of how fast the atoms or ions and electrons are moving or vibrating. So if you kind of were to zoom in on the atoms, or in your water bottle, or in the ions, the nuclei and the electrons in a star, all of those things are constantly in motion. Even things that we look at when you hold a baseball, it looks like the ball is at rest in your hand. Well, if you were to zoom in on the atomic level, all of the atoms in it are constantly in motion, just jiggling around. And the temperature of an object is a measure of how fast those particles are moving as they jiggle. Okay. So, for example, air molecules, which is mostly nitrogen and oxygen, are constantly in motion, and they move around at over 1,000 miles an hour. Okay. Now, fortunately, they're small, so when they hit you, they don't sort of knock you out. But that's the origin of air pressure. It's just these molecules constantly bombarding your body many times a second. Okay. So air molecules, you can't see them, but they're constantly in motion, and they're zooming around at over 1,000 miles an hour. Atoms in a solid don't move around nearly as much or as freely as the molecules in the air, because they're in a solid, so they're kind of locked in place by the repulsive forces between themselves and neighboring atoms or molecules. But nonetheless, they're constantly jiggling around, and so as I said, even those things that are solids where they look like it's just staying completely at rest, if you were to zoom in, at an atomic scale, you would see that these things really are moving. And the more you heat them up, the higher the temperature, the faster these things move. So just a couple of terms that I may have already used, but just to be explicit here, the random motions that I've just mentioned are called thermal motions, and the energy in that motion is called thermal energy. Now that we've defined the notion of temperature in a precise way, the next term that I want to introduce is one that I have already alluded to, at least in passing, in the last couple of slides, and maybe even earlier in the course, and that's the notion or the concept of absolute zero. So it turns out this is yet another example of a complete lack of creativity when it comes to naming. And so absolute zero is nothing less than the lowest absolute temperature, the lowest theoretical temperature possible. And you'll very often hear this defined as the temperature at which all particle motion stops. I say it a little bit differently because it turns out that that's not possible for reasons that are fundamentally quantum mechanical in nature. We're not going to go into in a lot of detail, and you can thank me for that. Though, as usual, if you want to know more about that, I'm happy to talk about it. But we can certainly say that absolute zero is the lowest possible temperature that is theoretically achievable. And you have removed, at that point, you've removed as much motion as is possible from the system. Practically, it turns out that it's not possible to get quite there, but we have come extraordinarily close in laboratories. So when we use an absolute temperature scale, which is what we are essentially always going to use unless I tell you differently in this class, we're going to measure temperatures in units known as Kelvin. So you may or may not have heard of the Kelvin scale before. You certainly are familiar with the Celsius and Fahrenheit scales. The Kelvin scale, or the absolute temperature scale, has a degree which is equivalent to a Celsius degree. So the difference between 1 Kelvin and 2 Kelvin is the same as the difference between 1 Celsius and 2 Celsius. But the difference is that 0 Kelvin means absolute zero. So to give you a sense of how cold that is, it's equivalent to 273 degrees Celsius below zero and change, as you can see here, or almost 460 degrees Fahrenheit below zero. So it's really cold. As I said, it's impossible to get there exactly in the real world, but we have gotten systems, in particular clouds of atomic gases, down to on the order of 50 nanokelvin, for example, which is 50 trillionths of a Kelvin. So, for all practical purposes, that is, that's extraordinarily close to zero, but we can't get quite there. A couple final notes here again. So Kelvin is the SI unit for temperature, which just means it's the standard temperature unit in physics and astrophysics and astronomy. And just to give you an idea, room temperature is about 300 Kelvin. So, again, we're not going to be plugging into a lot of equations here, but it's good to have some general sense of what the temperatures involved are. And so, as I said, unless I tell you differently for some reason, we're essentially always going to be referring to temperatures in Kelvin, and an absolute zero is just 0 Kelvin. So I mentioned a few slides ago that thermal motion is just the random motion of particles, whether atoms or nuclei, or electrons, molecules, whatever makes up the system that you're describing. As long as you're not at absolute zero, which is all the time, things are going to be constantly jiggling around. And if they're in a solid, they'll be kind of locked in place, but jiggling around some average position. If they're in a liquid, they'll be jiggling around while they slide past one another and flow. If they're in a gas, they'll be largely independent, as is shown here in this box, where you had just independent atoms or molecules flying around that don't know anything about each other, but they're moving around at some speed. And what that speed is, again, is sort of measured by the temperature. The temperature is a measure of the average speed of the particles as they move around in this thermal motion. Now, as you know, atoms are made of nuclei, these positively charged nuclei, thanks to the protons, and these negatively charged electrons. Now, since we're not at absolute zero, since we're at some temperature, some finite temperature, we've said that all of the particles are jiggling around. So if you think about a star, a plasma, or any atom, you have these charged parts, both the electrons and the protons in the nucleus, which are jiggling around due to the thermal motion. And as it turns out, and I mentioned this earlier, but I want to focus on it now, when you move a charged particle back and forth, it produces light. Okay, and the frequency of that light is determined by how fast you're wiggling this particle. So if a particle is wiggling around at 10 times per second, it's going to produce light that has a frequency of 10 hertz. Okay, now that's really low. That's you're definitely that's like extreme radio frequencies, very low frequencies for light there. So to generate visible light, you're going to have much faster, much higher frequency oscillations of the electron. But it turns out that electrons are really small. And by that, what I really mean is they have very low mass. And so it turns out that it's actually really easy to move electrons back and forth quickly. Easy for nature to do it. It's not, it's not like we grab it with tweezers, right? But it's easy in nature for very high frequencies to be realized. And it turns out you don't have to do a whole lot to get that. You just have to have some reasonable temperature, right? Because again, the random motions that these particles undergo in any non-zero environment, non-zero temperature environment, is going to produce these accelerations of electrons, and that's going to give off light. And the hotter something is, the more random motion you're going to get, and the higher frequency and the more light is going to produce. And this is, we're going to use this concept over and over and over again. This kind of sets the stage for certainly the rest of the lecture today, but really far into the future of this course, because this is the fundamental connection here between temperature and light. I say this over and over again, so I hope that by the end of the course this has been sort of drilled deeply into your gray matter. The goal of astronomy is to extract as much information as we can out of the light that we get. And this right here, this slide encapsulates the fundamental connection between temperature, this random motion, and light. The reason that those are connected is because when you jiggle charged particles, they generate light. And so let that sink in. Feel free to pause me and think about that deeply. But we'll move on, and we'll talk about this quite a bit going forward. Okay, so let's think about thermal radiation now, right? Which, if you break it down, just means radiation, electromagnetic radiation, aka light, which is generated from thermal motion. Okay, so again, thermal motion is just the random motion that is a natural result of a non-zero temperature. Okay, so we aren't imposing any motion here. We aren't making it do anything artificially. This is just the natural motion that occurs in nature due to non-zero temperatures. So, and as it turns out, a light bulb is actually a really good example of this. Light bulbs work, in a way that kind of goes along exactly with what we're talking about here. So we're going to draw a lot of spectra that look a lot like this now. We've talked about a few different spectra, right? We talked about continuous spectra, emission line spectra, absorption line spectra. Right now we're focusing on continuous spectra because thermal radiation produces a continuous spectrum. That's just a statement. If you want proof, I would love to give you a proof. The math is a lot of fun, and this is sort of a classic problem in statistical mechanics. But we're not going to do that. I'm just going to tell you right now that thermal radiation, because of the random motion of particles, it produces a continuous spectrum. And you can kind of think of that as arising from the fact that because you have a huge number of particles that are moving around, some are moving faster, some are moving slower, some are moving in intermediate speeds, and you basically have you have all different speeds represented in your object. You know, for us, it's normally going to be stars, but it could be a light bulb filament as well. And so because of that, you're going to get all possible frequencies, but not in equal amounts. And so what your spectrum is going to look like is very much like what I've sketched here. So let me take a moment first to describe kind of what I'm plotting, the way that I'm setting up this plot, because we're going to see a lot of these going forward. So on the vertical axis, we have the intensity, which, if you recall, is just how much power per second, or I'm sorry, how much power per square meter are you getting? So how much energy per area per time is being emitted here. And we're looking at that as a function of the wavelength. So low wavelengths are here at the left, which means high energy photons. Large wavelengths or low energy photons are here at the right. And I've kind of called out the visible spectrum here. And so what you can see is it's the spectrum starts off at 0, and that makes sense. Any spectrum has to do that when plotted this way, because 0 wavelength means infinitely energetic photons. Okay, we don't have any. There's no infinite energy, you know, either here or anywhere else in the universe, and so the spectrum is always going to start off at 0. Then it's going to rise, and it turns out that it rises relatively quickly in this case. How quickly depends upon the temperature, and you'll see more examples. But it rises to a peak, and then it falls off and decays here in this way. And so you see a number of different curves like this, both today and then moving forward. But they're all going to look very much like this. The differences are just going to be where they peak and how high that peak is, for example. This particular one peaks in the visible spectrum, right? So the greatest amount of intensity, the greatest number of photons that are being produced by this light source are being produced right around 500 nanometer wavelength in the green. Okay, so you've got a lot of green photons, you've got quite a few blue photons, quite a few yellow photons, you've got a little bit less red, but there's certainly some red. And it's important to call out too that you have quite a few photons that are outside of the visible range, right? You have some ultraviolet photons, not a lot because this falls off very quickly here. But you certainly have a lot of infrared photons. I mean, look at all of the intensity that is here outside of the visible spectrum. So since we're stuck with eyes that only register in the light in the visible spectrum, we're going to see the color of an object as determined by what the photon distribution is, or what that spectrum is in the visible range. But it's important to remember that there's plenty of light coming outside of the visible range as well. And fortunately, we've learned as astronomers how to detect that light and extract information from that part of the spectrum as well. So for this particular curve, it's characteristic of an object at 6,000 Kelvin. So T here is the temperature. It's equal to 6,000 Kelvin, and the peak wavelength is 480 nanometers. Turns out that's not just a randomly chosen temperature. That's very close to the surface temperature of the sun. So this is very nearly the spectrum given off by a black body, we would call it, or due to the thermal radiation of something whose temperature is the sun. If we pull that back, if we were to cool off the sun, for example, by just 1,000 Kelvin, so instead of 6,000 Kelvin, we bring that down to 5,000 Kelvin, you see the curve changes, and it changes quite a bit. And it changes in two significant ways, right? The first is that the curve gets pulled down significantly, so the total intensity is much lower, and we'll say more about that in a little bit. The other thing that happens is that the curve shifts out to the right a little bit, shifts towards larger wavelengths. And so instead of the peak of the spectrum being at 480 nanometers, here in the green, we've shifted the peak out to 580 nanometers, which is in the yellow to orange part of the spectrum. Okay. So again, keep in mind, we'll see this over and over, but keep in mind, as you have now dropped the temperature, there are two main things that happen. One is that the total intensity falls by a lot, And the second is that the peak of that spectrum shifts out to larger wavelengths. If we bring it down another 1,000 Kelvin, the intensity drops even more, and the wavelength shifts out even farther. And in this particular case, at 4,000 Kelvin, you can see the peak wavelength is at 730 nanometers, which is right on the edge of the visible spectrum. So you certainly, this is very much still a visible source, right? Because you can see there's a lot of visible light being still being given off. Plenty of red, plenty of orange and yellow, less green, but it's still there, and even a little bit of blue. But the fraction of the light that is infrared is larger than it was before. And then finally, if you drop it down to 3,000 Kelvin, you have very little visible light being given off, and a peak wavelength that is well into the infrared. Okay, and so this kind of starts leading us towards a situation. 3,000 Kelvin is still much warmer than your body or mine, but it starts giving us a hint of what the spectrum would look like for one of our bodies, right? We talked recently about infrared radiation that you and I give off, and how night vision goggles are able to capture that and convert it into the visible range. You can see that compared to the intensity or the spectrum of the sun up here at 6,000 Kelvin, the spectrum from a 350 Kelvin object or something like you or me would be much less, right? Which is not surprising. We're not stars. But things that are much colder than the sun do still give off visible light, and so an electric burner on a stove is just one example. So everything that's not at non-zero temperature, absolute temperature, gives off thermal radiation. The only thing that determines whether we can see it or not is whether there is enough radiation being given off in the visible spectrum for our eyes to register it. So if you look, for example, at molten iron, it's in the red, which means you may be used to thinking of red as being a warm color, and the artists tell me that it is. But from a physics perspective, that's the coolest color there is, but still much hotter than you want to be in contact with, right? So molten iron here glows red, and it has a particular blackbody spectrum then that peaks somewhere in the red part of the spectrum, right? And as it turns out, it's worth mentioning too that as you move from the red towards the peak of the spectrum, as it moves from the red end of the spectrum towards the blue, things are getting hotter, right? And we'll say more about that in a minute. But it turns out that white hot it's certainly hotter than red hot, but it's cooler than blue hot. Okay, and that's true of any object you like. Certainly is true about stars, and so for example, blue stars are the hottest stars that there are. A white star or a white anything, something glowing white hot, is white because it has very nearly the same number of photons being produced at all visible wavelengths. It can't be exactly equal, but it's equal enough that when our eye kind of puts it all together, it registers as white. And so you can kind of see an example of a white spectrum down here, where you have very nearly the same number of photons or equal intensity at all wavelengths. Whereas as you get even hotter than that, the peak of this spectrum is actually in the ultraviolet part of the electromagnetic spectrum, outside the visible range. But you can see there's more purple and blue photons, more energy in those wavelengths than there are in yellow and red, and so that object would appear blue. So here you have a burner here, and if you look in a fire, next time you set up a fire, either in your fireplace or somewhere else, take a look, and you can see different colors in different parts of the fire very often. And so again, the red parts, the orange parts, will be actually the cooler parts of the fire, whereas if you see a bluish part, then that will be hotter. So now you know. So I've used this term blackbody radiation a couple of times, and essentially it just means an object which is radiating with thermal radiation in thermal equilibrium. So which again means the temperature is constant, it's radiating energy, but it's also absorbing energy or producing it through, for example, nuclear reactions at equal rates. So the total internal energy is not changing and the temperature is staying constant. And so any of those, any black body spectra looks like this, okay? And again, the only thing that changes is as you change the temperature, the height of this curve, the total intensity in the curve changes, and where it peaks changes. But otherwise, they all look very, very similar, and you should have no problem drawing these. So, to summarize again what we've said, and to put it explicitly on the slide, hotter objects are more luminous, right? And that just means they have more intensity. They're producing more energy every second. So the hotter an object is, the more luminous it is. Luminosity, as a reminder, is the total rate at which energy, and in this case we're talking about electromagnetic energy or light, is emitted by an object. And so luminosity is measured in units of watts, which it's equivalent to power. So if you happen to take a physics class and you heard about power, luminosity is equal to the power radiated by an object. But it's just the rate at which energy is given off. How much energy per second. So in addition to hotter objects being more luminous, they're also bluer, right? So I'm just putting in different words what we've already said a couple of times, which is that as you heat up an object, the spectrum is going to shift up. It's going to get taller because the total intensity is higher, and it's going to shift towards the blue end of the range. Okay, so as you heat this object up, the curve shifts up and to the left in this kind of plot. Now, so far we've just described these things qualitatively, but it turns out, and this may not come as a shock to you, but there are quantitative laws that you can write down as well. There are equations that are relevant here. And so to start off with, in order to describe the luminosity of an object in a quantitative or a mathematical way as a function of its temperature, we can use something known as the Stefan-boltzmann law. And a simple way of writing that is given here, where the luminosity is proportional to the fourth power of the temperature. And so you may or may not have seen this symbol before, just reads is proportional to, and so it means, in this particular case, the luminosity is proportional to the fourth power of the temperature. Now what does that mean? Well, it means that if you were to double the fourth power of the temperature, you double the luminosity. If you were to triple the fourth power of the temperature, you triple the luminosity. But what's this deal with the fourth power? Well, to make a long story short, it means that the luminosity increases a whole heck of a lot if you increase the temperature even a little bit. And we'll say a little bit more about that in a second. So before I have you actually answer this question in detail, I want to say one more word about the temperature to the fourth power. So the fourth power just means that you multiply the temperature by itself, by itself, by itself, 4 times, right? So if the temperature were 2, if it were 2 Kelvin, you would take 2 times 2 times 2 times 2, right? And so that would give you 16. If the temperature were 300 Kelvin, then you would take 300 times 300 times 300 times 300, and you would get a big number. So the fact that you're taking 4 powers here, 4 times you're multiplying the temperature together, is what's responsible for this very strong dependence. So again, if you increase the temperature just a little bit from, say, 500 Kelvin to 600 Kelvin, or as we saw in the last slide, from 5,000 Kelvin to 6,000 Kelvin, you're now multiplying that new larger number by itself 4 times. And so the luminosity grows very quickly with the temperature. So here at the right, we have a particular example. So let's consider that we have 2 light bulbs. One bulb has a temperature of 1,000 Kelvin, and the other bulb has a temperature of 2,000 Kelvin. How many times more luminous will the hotter bulb be? So as usual, I'll pause here for 30 seconds or so. You're welcome to pause me longer, and then we'll come back and we'll talk about the answer. Okay, so as we said, the key to the Stefan-boltzmann law is that the luminosity is proportional to the fourth power of the temperature. So in this case, what does that mean for us? Well, the second bulb is twice as hot as the first bulb. The temperature is twice as high, which means that the right side of this equation, this T, has been multiplied by 2. But now we're going to multiply that 2 by itself 4 times, right? So 2 times 2 times 2 times 2 is equal to 16. And so the upshot is that you only doubled the temperature of this light bulb, but the luminosity went up by a factor of 16. And so this is really, I can't emphasize enough, though I will emphasize it quite a bit, both today and then as we go on in the course. The luminosity is what we're observing, right? That's the brightness. It's very closely tied to the brightness of what we observe. And so, if you double the temperature of a star, then the luminosity is going to go up by a lot, by a factor of 16 here, right? And so that's something that we're certainly going to keep in mind going forward. One thing that's important to know, though, is that while the luminosity is a great quantity for physicists, when we calculate the properties of stars, we love to calculate luminosity, and that makes a lot of sense. It's easy to understand. It's the total energy being sent off into space. The problem is when it comes to measuring things, that it's pretty darn difficult to measure all of the energy being produced by a star, right? You would have to somehow build a spherical shell of a detector that completely enclosed the star. So that's not something that we're going to be able to do. It's much easier to measure something that's called the flux, or the intensity, which is the luminosity per square meter of area. And so for that, we can rewrite the Stefan-boltzmann law and say, since we're not going to be able to measure the total luminosity, we're actually going to measure the flux, how much energy, or how much energy is passing through a square meter per second. That we can measure with detectors. And so we're actually going to change this proportional to sign into an equal sign. And we do that by introducing a constant here, which is known, again, not very creatively, as the Stefan-boltzmann constant. And it's just a number. It had to be measured the first time, and there are probably still some people out there that try to measure this and add even more digits to it. But this is plenty good for us. It's 5.67 times 10 to the negative 8 with appropriate SI units. And so, if I were to give you the temperature now of an object, say, you got something at room temperature, 300 Kelvin, what's the flux of electromagnetic radiation it's giving off? You'd just be able to take your calculator, plug in the numbers, and you would immediately be able to calculate the flux. And that's great because, again, this is something that we can actually measure. Okay, we can't measure how much total energy is being given off by the sun, but we can measure how much energy is getting to us from the sun, in a square meter detector. So we've said hotter objects are more luminous. We've said hotter objects are bluer. And now we have a quantitative expression for the luminosity here as it relates to the temperature given in terms of the Stefan-boltzmann law. But there's another aspect of the spectrum that we have already talked about, but we haven't quantified yet, and that's where the peak of the spectrum is. We said that hotter objects are more luminous, and the Stefan-boltzmann law tells us exactly how. Well, hotter objects are bluer as well, and it turns out there's another law that tells us how that works, and that's known as Wean's law. So, if you have ever wondered how to describe or how the temperature of an object is related to the peak wavelength of its spectrum, Wean also wondered that, and he solved that, and here's the answer. So in order to describe how the peak wavelength of an object's blackbody spectrum relates to its temperature, we can just plug into this equation. And so you can see it's a pretty simple equation. You've got a constant up in the numerator, which is just some number with units of nanometer Kelvin. And then if you measure the spectrum and determine what the peak wavelength of that spectrum is, you can divide this number by that wavelength, and that gives you a temperature. And so, this is exactly what astronomers would do if they look at a new star and they ask, okay, well, what's the temperature there? They collect the light, they used a spectroscope to split it up into its component wavelengths, they plot the spectrum, they identify where the peak is, and then they plug in here and they calculate the temperature. Easy as that. So, for example, what is the peak wavelength of a light bulb with a temperature of 1000 Kelvin? We don't do a lot of calculations here, but this one's reasonably straightforward. And so I'll go ahead and throw this one at you, and I'll pause for 30 seconds, and then I'll tell you. Okay, this is a problem that if you're really crunching the numbers, by all means, feel free to pause me. And you may, hopefully you won't be too mad at me, because actually these answers are in different units here, and so there's a little bit of a unit conversion at play here too. So again, if this were a class in which we did a lot of calculations, I would go into a lot more detail, showing you exactly the steps involved here. But for now, I just want to focus on sort of the high level, applications of the equation here. And what we would do in this case, we're given the temperature, right? And the question is, what is the peak wavelength? And so we're actually looking to solve for lambda here, the peak wavelength, given the temperature. And so it's one step of algebra, right? You multiply by lambda peak and you divide by the temperature, and you find out that the peak wavelength is equal to this same number divided by the temperature. The temperature is 1000, which makes the math easy. And so you're left with 2.9 times 10 to the 6th divided by 1000 Kelvin. That ends up giving you 2.9 times 10 to the 3 nanometers, which is the same as 2.3 microns, or micrometers. So just as a reminder, or maybe first time you've heard this, a micron or a micrometer, which is denoted here with mu m, is just 1000 nanometers. Okay, so 10 to the 3. So again, we're not going to do a lot of calculations. If you want to see all the steps or talk about this in more in depth, certainly get a hold of me, and I'll be happy to talk about that. The important thing here, though, is that there are quantitative relationships that embody or encapsulate and capture the two observations that we've made about spectra. So now we know the Stefan-boltzmann law tells us how the total luminosity, or the intensity, is related to the temperature. And now Wean's law tells us how the peak wavelength of the spectrum is related to the temperature. Now, as we approach the end of this lecture, I want to make a connection with something that is even more important for actual astronomers than either luminosity, than on luminosity, and that's brightness, and it's a term that I've used recently as well, because it turns out that, again, physicists love things like luminosity or intensity because it's very easy to calculate and straightforward to understand. But we're stuck here on Earth, as I continue to harp on, and so when we look up at a star, some stars look bright and some stars look dim. But unfortunately, there are two reasons that could be that a star might appear bright. For example, it could be that that star is extremely luminous, is really giving off a whole lot of energy, or it could be that it's just an average star, but it's really close, right? And so, unfortunately, brightness depends upon both luminosity and distance. And so, as astronomers, if we're going to try to extract as much information as we can out of this light and figure out, okay, how hot is that star? We're going to have to disentangle these two effects. And we see this all the time, right? This is not something peculiar to stars. The brightness of cars' headlights depend, on distance, certainly. If you see dim headlights, you probably think that means the car is far away, but maybe it just means the headlights are almost dead and it's getting, this car is getting ready to crash into you. So, in the spirit of continuing the quantitative descriptions of things, let's try to understand first, why does brightness decrease with distance? And it turns out, I don't know if you've thought about this before, but it turns out it's not rocket science. But if you wanted to give it a fancy sounding name, it all comes down to conservation of energy, right? So let's think about the energy that leaves a light bulb in a second. Okay, every second, some amount of energy is emitted by the light bulb, and it's emitted in all directions. So it spreads out in a spherical shape, as is indicated here on the slide. The amount of energy that was emitted in that second never changes, right? So let's say if it were a 100-watt bulb, for example, that means it's giving off 100 joules of energy every second. A joule is a unit of energy. It's the standard unit of energy in the SI system. We're not going to focus on that right now. It's the unit that we're going to use. So if you have a 100-watt bulb, it emits 100 joules of energy every second. But then that light travels out in ever increasingly large spheres. And so at some point, that light has traveled a meter, okay? And now you have 100 joules of energy spread out over a sphere whose radius is a meter. A little bit later, it's traveled out to a sphere of radius 2 meters. So now you have exactly the same amount of energy, but it's spread out over a larger sphere. Go a little bit longer, now the radius of the sphere is 3 meters. And the area of that sphere is even larger. So the reason that the intensity or the brightness of that light decreases is just that you have a fixed amount of energy and it's being spread more and more thinly as that area increases. And for those of you that remember your high school geometry, the surface area of a sphere is equal to 4 pi r squared, where r is the radius of the sphere. And so what that means is, since the total energy that's being emitted every second is fixed, but the area is getting bigger as a function of r squared, the radius squared, that means that the brightness is inversely proportional to r squared. So in other words, if you double the radius, the brightness falls by a factor of 2 times 2, or 4. If you triple the radius, the brightness falls by a factor of 3 times 3, or 9, and that's it. So, and just to kind of say that in another way, if a light bulb were producing 100 photons per second, so instead of 100 watts, it were 100 photons per second, the exact same logic follows. You're taking those 100 photons and you're spreading them out over larger and larger areas, and so the brightness is getting smaller and smaller. And since, we're all about quantitative analysis, or at least quantitative descriptions to show you that there is real rock-hard mathematical science behind all this, we're going to throw up an equation here too. And it really just captures everything that we just said in the last slide or two. The brightness here is just equal to the luminosity divided by the surface area of the sphere, right, of this imaginary sphere over which the light has spread out. And so, as I said, the area of a sphere is 4 pi r squared. So if d is the distance from the light source, either the light bulb here or the sun or Alpha Centauri or whatever you like, then the surface area of this imaginary sphere over which the light has spread itself out is equal to 4 pi d squared. So L is the total energy per second that's being produced. That's the luminosity. Divide that by the surface area, which is just the total area of this imaginary sphere, and that gives you our definition of brightness. And so this kind of captures, just to kind of put the final nail on the coffin, we started off by saying that the brightness of any object, for us largely stars, depends upon both luminosity and distance. This is the mathematical expression of that. And so, again, our job going forward is going to be how can we sort of disentangle these things and figure out, hopefully, both how luminous is the star actually and how far away is it. So to sort of solidify this, hopefully, let's look at the following example. So how many times fainter would the sun appear on Jupiter as compared to the Earth? Okay. And I'm going to tell you up front, because if I didn't tell you, you would have no way of answering this. Jupiter is located 5 astronomical units from the sun. If you've forgotten what an astronomical unit is, this is a good time to pause me and go look it up. I could just tell you the answer, but then you probably wouldn't remember it. But Jupiter is located 5 astronomical units from the Earth. So how much fainter does the sun look? So I'll pause for 30 seconds again, and then we'll come back and finish off the lecture. Okay, so hopefully if you didn't remember what an astronomical unit is, you did go look it up. It's just the distance between the Earth and the sun, right? So this parenthetical statement here is the same as saying that Jupiter is 5 times farther away from the sun than the Earth is. And the question is, well, how does that impact the brightness of the sun? Well, if we go over to the equation, or if you don't like equation so much, you can skip back to the previous slide and look at that sort of schematic with concentric spherical shells. And either way, the dependence here is this inverse dependence on the distance squared, right? So since Jupiter is 5 times farther away, we're going to square 5, which means multiply 5 by 5, which is 25. And since that's in the denominator of this fraction, that means when you're calculating the brightness of the sun at Jupiter, you get the same luminosity because the sun is the sun, right? So whatever energy per second the sun is giving off, that's the same number. The only difference, if you're calculating the brightness on Earth or the brightness on Jupiter, is that D is 5 times bigger on Jupiter. So you're dividing by 25, and that means that the sun is 25 times fainter on Jupiter than on Earth. So as much as I would love to continue throwing more equations at you, I think that's probably enough for today. So I appreciate your attention. Hope you learned something, and I will look forward to seeing you back for the next lecture.